Emerging Trends by Bob Wall. Our moderator for this session is Melanie Wingo, and this session is worth 1 CEU. As a reminder, as you all know, the chat box is used for your networking and collaborating, and the Q&A will hop up about 15 minutes before the session is over. And as a reminder, this is being recorded, and I will turn this over to Melanie for an introduction of Bob.
Thanks, Megan. My name is Melanie Wingo. I am one of the 7 traffic safety liaisons in Illinois. I've been a technician and instructor since 2002, and it is my pleasure to introduce Bob Wall. He's a nationally recognized public safety professional and has been a leader in the CPS field for over 30 years. Bob, along with a dedicated group of CPS advocates, came together over 25 years ago to develop and co-author the national standardized CPS curriculum that is still used today to certify CPS technicians nationwide. Bob joined the Nuna team in 2012 and introduced the PIPA infant car seat and base with a load leg, one of the first of its kind in the United States. He serves as a resource and educator on car seat safety for the Nuna team and others across the country. Welcome, Bob.
Thank you very much. So we're going to talk a little bit about what's going on in the community as far as engineering and design and what's coming up and what's here to stay and all those things. I hope you can hear me. So somebody give me an indication. I'd say raise your hand, but I can't see anybody. So can everybody?
We can hear you. We're
okay,
good, Bob.
Great. So first of all, we're going to talk about energy management. And the reason why I call it energy management is because, people, and I know that a lot of the people who are law enforcement understand, you can't predict or you can't control energy. You just have to manage what it does to the body. So what we need to talk about is, how do car seats do just that? How do we manage an energy that is so great that it could kill us or the child or whatever? So we started looking at stuff, and we looked over the years, we looked at different designs. And yesterday, Brian Witt from Evenflow did a nice presentation on how things are designed, and he talked about past trends and what people are looking for and things like that. And when it comes right down to it, the bottom line is, what's saving our children? Well, Paul Goudreau and Vera Fullaway and I got together and said, well, we need to work on maybe teaching people what these things really are and how they really do protect children. The one thing I have to say about technology is it changes every minute of every day. As we speak, there are new technologies being designed for energy management or ease of use or whatever it is, whatever the trend may be. As Brian said yesterday, there's a lot of reasons why things change and things evolve. But when you think about it, energy management's been around for a very long time. In the very first curriculum, there was a picture of what the picture said, foot prop, and it was a Volvo child seat from Europe with a foot prop that went down to the floor. And the title of that slide said, "Coming to America Soon." Well, that was over 25 years ago. And for the next 20 years or 15 years, those foot props or load legs or stability legs or whatever you want to call them really did not evolve here in the United States the way they did in Europe and other places, because they just weren't accepted as part of practice, nor were they part of our standard. But they did do something, and that is they managed energy. So when you think about it, we'll go right back to, again, Brian's presentation, even if you didn't see it, he talked about, what do we look at when we design car seats? And the first and foremost is, does it meet the standard? Well, The standard is based on crash data. Okay, so what are children most at risk at? This morning during Julie's workshop from Ohio, her comment was she talked a lot about data, and in some cases there's not enough data to actually point to a problem or an issue of concern because there's not enough data, there's not enough points. Well, when it comes to crashes, we got plenty of those. So when you look at the crash data and look at the percent of crashes versus injuries to children per 1,000, the biggest crash risk is obviously frontal. Well, that's our 213 standard. So 213 is modeled in a frontal crash scenario. And it basically is a 30-mile-an-hour crash into a fixed object, because that is the most common of crashes. Now, if you look at this is the blue lines are the most common crashes. The green lines are the most injury. Look at the bottom. Rollovers, 78% of per 1,000 children are injured because of a rollover crash. But they only account for 2% of our total crashes. So the risk is not as great. So when you look at where money or design effort is put into certain products, we have to look at all this data as well as marketing, as well as ease of use. It's all part of the process. And the big process is, how do we manage what happens to a child in a crash? So when you look at this, and again, I'm going to refer back to this data point a lot. Obviously, the most risk is frontal and then rear end. But rear end, look how low the data is for injuries. It's actually the lowest because, said in an earlier workshop, rear end crashes are usually not as severe. They're usually the same direction, or there's braking involved, or there's a lot of different factors. But also the injury reduction is there because the seats that we currently have do a great job of protecting children in those crashes. Same thing with frontal. Look, 40% and only 9.5% injury rate. So we're doing a pretty good job in the most common stuff. Then we look at the side impacts. We got near side and far side. Obviously, near side is higher because there's intrusion. Far side is about par with frontal. Okay, but you'll notice still the exposure is much different. Just like rollovers, the exposure is much different. Now, there is a seat that has been tested using a rollover type crash that they developed. Evenflow has a rollover seat that was tested in a rollover simulation. Just like everybody in the child seat manufacturing field has side impact crash tests. There is no standard quite yet, and the government says it's going to be here, and there is a proposed side impact. But what's been happening is we're using the European models that they have a side impact, and we're doing our own side impact crashing. So there is a proposed side impact crash test, because you'll notice they're basically up there as far as number of children killed or injured, and we have to have something. So it has been an issue, and you'll see every car seat manufactured has some type of side impact pattern or crash negation. So again, when we're talking about the emerging trends that have been coming for the last few years, okay, and basically we look at load legs or stability legs and anti-rebound bars or panels, and also just energy management designs in the seat themselves. So you'll see a lot of seats that have different pieces that are there that look sometimes kind of strange, but they're there to absorb the energy in a crash in either a frontal or rear or whatever, or both. So we're going to talk about these trends and what they look like. Now, one thing that I will say, our 213 standard does not regulate stability or load legs or anti-rebound bars. Okay, it does not. It also doesn't regulate any other type of energy management. It does not say you have to have X, Y, and Z to make the data say this. They just give us a performance standard. How you meet that standard could be a number of things. Now, the biggest problem with introducing some of these things like load legs and anti-rebound bars, there is no testing procedure for those. There is no standard for those. There isn't even a floor in the 213 bench currently. So testing a stability leg or a load leg becomes problematic and also very expensive. So that's another reason why it's taken a lot of time to kind of migrate to the US. It's an extra cost that people were just not willing to put into it. So think about it. What are the 5 things a child seat does? Go back to our child seat class. Go back to the standardized curriculum. Keeps the child in the car. It contacts the strongest parts. It spreads the forces over a wide area of the body. Sounds like crash energy management, right? Helps the body to slow down or ride down the crash forces. And it protects the vital organs, the head, brain, and spinal cord. And this morning, if you saw Julie's presentation this morning, she did a great job of talking about how we need to protect that head and neck and spinal cord. And even head injuries lead to spinal cord or neck injuries just from the impacts. So again, what does a child seat do? The first thing it does, keeps them in the car. And then the rest of this is all basic energy management. But how do we manage it even better through design? Whoops, wrong direction. So the thing is, all of these trends that are you starting to see, there's a lot more seats out there that have a lot more things on them. All of them are proven trends that are now being introduced into the US. So load legs and European belt routing, which is the routing where the shoulder belt goes around the back, and anti-rebound bars, they're all designed to reduce the transfer of energy to the child, resulting in less injury. And there are places in Europe, legs are standard. Legs are standard in many places. Rebound bars are standard in Australia, in Canada, in other places. Now, do they do what they're supposed to do, and what is it they're supposed to do? So when you look at, let's talk about legs first, okay? The stability leg is the big thing that you're going to see on the shelves the next year or two. I almost think every child seat manufacturer, except for 1 or 2, actually have a seat with a leg or working on a seat with a stability leg. And the reason why is because people are demanding a little bit extra safety for their child. Also, because of that demand and the design features that other manufacturers have done, not as expensive anymore. At one point, when ISOFIX or the latch system was introduced into the United States, everybody said, well, let's just do the same one Europe has. Well, it was heavy and expensive, and it was going to cause probably less child seat use. So we had to come up with a hybrid, which we now call latch. But that hybrid didn't include a leg, which the European does. So do we use a leg? And the question would be, it's up to you. It's up to the manufacturer. Do they want to take that extra step to design it in, a lot more money, a lot more testing, and then the parent has to put up that extra money. But I will say this, Evenflow now has a child seat with a stability leg. It's under $300. It's under $200. So it's becoming affordable. Okay, it is becoming affordable. These energy management tools are doing just that. They're becoming affordable, and they make a huge, huge difference in injury data. Okay, so what it does is it supports the part of the seat or the base that extends from the base to the floor, and it can provide additional stability. And what it does is it absorbs the energy and it stops that rotation. Now, unfortunately, as one of the very first instructors, we didn't do a great job of talking about rotation. We talked about rotation as ride down, and people really thought that the rotation part was the ride down, and that is not true. Okay. The rotation is just extra motion. And that rotation, there is no ride down until that rotation stops. And then the energy is transferred or ridden down through the seat. And the energy goes down through the seat, across the baby's back, into the plastic shell, and through the floor of the vehicle, through the leg, whatever. Okay. That's when the ride down begins. So all that other stuff is just extra motion. So the goal is, how do I start ride down quicker? I reduce the rotation forward. All right. And to do that, you would use a leg. So the leg starts that ride down process much sooner. Okay. So it limits the initial movement toward the point of impact, which reduces not only rotation and injury to the child, but it also reduces rebound. We haven't even talked about rebound things yet. All right. So what it does is, because we've taken, and somebody told me this one was great. If you take the wind out of its sails going this direction, there's not as much energy going the other direction. And actually, Julie this morning talked about that because they did a study at the Ohio State and talked about, they didn't find a lot of data that says there really was a lot in either rear end or rebound crashes that showed a significant need or a significant pattern of injuries because of rebound. Child seats are doing a good job because what's happening is they're either reducing that initial energy, which then takes some of the energy out of the sails, or it's got a sturdy enough base, or a base that is actually up against the seat enough, or it's sturdy enough or installed it well enough that it doesn't come all the way to the back. And there is no striking of the head or injuring of the head or neck and spinal cord. So what it does is it decreases those forces on the baby's head. So when you think about what a leg does, okay, it reduces the rotation. Sometimes it reduces it by 90% or more. If I can start that rotation or stop that rotation quicker and start the ride down quicker, that's potential for less injury to the child. So when we look at the data in a crash test, we look at HIC values, which is head injury criteria. And we can find, in just one of our tests we did for 213, we saw almost a 40% reduction in that number using a leg versus not using a leg. So if I can reduce injury values to the child's vulnerable parts, the head and neck, by 40%, that's what I really have to think about. Now, here's our standard base. It is just a leg that goes down and touches the floor, and all it has to do is just stop that rotation. But it also reduces the rotation backwards because we've taken the energy and distributed it. So let's look at some crash tests. This is a standard seat, typical car seat rotation without a load leg. This one starts at 40 degrees, 40.45 degrees vertical, and you'll see the yellow lines are obviously vertical. And then the second yellow line that's at an angle is the starting angle and the apex angle, the angle where it's the furthest into the crash. So we start at 40.45, and at full rotation, it's just a little bit over 63 degrees from vertical. So it has about 23 degrees of frontal rotation. Guys, that is a 213 pass. It's not a, less is better. It's a pass fail. 213 is a pass fail. If it goes over 70 degrees, it's failed. If it's under 70 degrees, it's a pass. So this is a pass. It passes the test. So we look at, here's our original PIPA, rear facing, without a leg, without the use of the leg. And somebody asked in the last workshop, is the leg optional? Yes. It's not required in the US. It's not required to be tested. It's not tested, but we have to test it to make sure we're doing our due diligence to make sure that it passes in all modes. But we do test it with and without. This is without. So we look at this without a leg. It starts, our starting angle is usually about 36 degrees. Okay, 36.12 degrees. We do it very specific. And at full rotation, we get to 54.6 degrees. So it had about 18 degrees of rotation. And you can see in the two pictures, all right, the targets in the back, the lines and the targets, it shows you how it's reclined and covering up the first and the second target. Okay, if it came down any further, another 20 degrees or so or less, the top of that seat would be toward at that third target almost, okay? And it would be a fail. This is a passing test. So what does it look like with the leg? So again, we have a test with the leg, okay? And this is a 213 test that we did, and I had to pick this one because it was a great one. And it started at 36.28, and at full rotation, it's at 36.28. Guys, it didn't rotate because the leg kept it in its place, in its place. Is that the norm? No, there's going to be a little rotation possibly, all right? But this just shows you how well that leg does. You can still see that there is movement because there's the three targets in the back. And you'll notice in the bottom picture, it's just barely touching the first target, all right? It's the same crash scenario as the other one without the leg. It just doesn't rotate. So the crashing, the energy, and the ride down started much quicker. So here's what it looks like. And don't blink because you'll miss it, but it is in slow motion. All right, so this is, and it's going to go over again. This is a crash test in slow motion, and it's 30 miles an hour, and you'll notice that it has the leg. Now, you'll notice that blue piece on the floor, that has to be put in. All right, we have to have that configured by the test facility to simulate a floor, because none of the test benches in the United States have a floor. There has been several petitions to say we should put a floor in. However, those petitions have been turned down. So again, this testing is, whoever the manufacturer is paying for this their own dime. There is no, it's extra on top of what they already do. But you'll notice it's even hard to see if this thing's moving except for the kid's feet, the dummy's feet. Right? So again, very little motion, very little, if any, rotation at all. Okay, so how does that leg equate to less rebound? Okay, all right, that test, we look at it, we say, okay, here's our rotation, and here's the rebound. You'll notice in the picture above, the legs are moving, so obviously this is mid-crash. It's actually on the way back. So the child seat is now rebounding back toward the seat. And at 66 milliseconds, the seat is rebounding back at, it's a negative, but it's at 0.13 degrees. Guys, because of all that energy that was scruffed off at the beginning and the placement of that leg, there is less rebound, which means less exposure to head and neck injury. Okay. So again, part of that, even with the leg, there would be very little rebound because of the making of the front of that seat, or where the child's feet are. So in basic, if you look at here, it's a CAD drawing of our newest base, and based on 213 testing, all right, the seat is more stationary during a forward impact, and it reduces the forward motion up to 90%. And it decreases the head injury values up to 33%. And I have a little note there because that's the average off all of our crash testing using the 213 standard and turning it into NHTSA. Other data shows it's closer to 40%, but that's over time. That's over a lot of different tests. And what it does is it maximizes ride down. And that's what we have to understand, what ride down really is. Ride down is not the motion, the rebound, or the rotation going forward. It's not starting until the seat stops. Now, I told you that there are a lot of seats now that have stability legs or load legs. And here's just a few of them. And, we got Evenflow has them, and Cybex has them, and Kleck has. They're all over now. There are a lot of them still being worked on. So again, this is one of those things that it's here, and you're going to have to know about it, because people are going to say, okay, what do I do with this? How do I make this work? So when you look at, say, the Nuna, which I just presented, very short presentation because I messed up with time, the relax base with our stability leg is just that. And it incorporates a newer stability leg that gets shorter for the vehicle middles that have large humps and makes it longer for pickup trucks. It also has an adjustable rigid anchor that goes in and out that not only swivels, but once it's attached to the car, you can push it in toward the vehicle back, and it will tighten it up, or it will snug up that lock off, which we also acts as a rebound panel, into the back of the seat. The one thing this piece does is it makes a heck of an install. It makes one of those rock solid installs that you really don't have to work at doing. So again, ride down. People misunderstand ride down a lot. They think it's the motion does this, and the reason why it's rotating is because it's riding down. No. We need to increase ride down by stopping the seat. All right. So increasing the stopping time can reduce the risk. So in other words, stopping it from rotating, stopping it forward facing with a tether. It's an energy management tool, a tether. That's been around forever. So let's talk about this misconception of ride down, okay? This is a computer simulation of a forward-facing seat, and basically, we talk about how a seat moves forward. Now, this says loose harnesses, installation, vehicle belts, stretching, foam. Guys, payout is basically everything that happens before everything stops. And if you think about it, using this simulation, okay, and I don't know if you can see my arrow, but I've got kind of messing with it on the screen here. If you look at this, we've got our basic vehicle bench, okay, and you'll notice all this deformation of the lower part of the seat. Well, what that is that's part of payout. So as the child has a forward-facing crash, all right, everything moves forward. The seatbelt, even though it's tight, it actually stretches. Now, if it's loose, it's even worse, because then it's loose and then it stretches. So This simulates, believe it or not, and it looks loose there, but it is a tight install. But what happens is it stretches out, and that's called payout. There's also payout in the harnesses. The harnesses will stretch out. And when the child actually hits the harness, the seat starts to stop that energy. So all of this, the seat pad, the stretch of the foam compression, all of that is called payout. Now watch real close during this next one. You'll notice the spine of the seat, when it turns red there, that's where the ride down begins. That's where that seat starts to absorb some of that energy. But look how far forward it goes first, okay? Because it still has to do the payout. And this morning, Julie talked about injuries to legs and how parents all just, crazy about, well, their legs are facing the back and they seem to be crunched up and they're going to hurt their legs. And she talked about, we see, even though the number's like negligible, it may be even the same, there's still just as much potential for leg injury, forward facing as rear facing, and maybe even a teeny bit more because their legs are exposed and they're coming forward, and all that payout, if we have too much of that forward motion, their legs are going to hit whatever's in front of it. So again, payout or that motion is not ride down. So you want the child coupled as tightly as possible to the harness system and the car seat coupled to the vehicle tightly, all right, with the seatbelt or the lower anchors, the latch. And when you do that, you gain the benefits of ride down. If you're loose, you're not going to get that benefit. Okay, you're not getting that benefit. So even though I say tight, I also want to caution everybody, it has to be reproducible. Remember, in a crash test lab, we have to be realistic, okay? They only use between 13 and 15 pounds of pressure to put a seatbelt in a child's seat for a crash test. So what is tight, okay? Guys, it's tight, all right? Has anybody, and I wish I could see everybody, anybody seen people do this with car seats? And I know everybody's going, yep. How many people had somebody come over their shoulder and say, hey, I can get that tighter? All right, it's usually a policeman or a fireman. And they're saying, I can get that tighter. Guys, yes. Okay, it's not an Olympic sport. All right, we want it tight, but we also want it to be reproducible. And we don't want it to damage either the vehicle or the child seat, because then we've got nothing. We've got an expensive paperweight that's broke. So if you think about our tolerance levels, our curbside tolerance and our testing tolerance levels, they use 13 pounds of pressure total. That's it. Nobody puts anything in the seat. Nobody. But guess what? There are many things, many that are designed to help with both installation and energy management all at the same time. It takes out some of the payout. All right, it takes it out. So if you think about this, all right, yeah, we want it tight because here's the data. If you have a crash, the auto hits about 20 Gs. Okay, now G-forces on the chest are a thing when you start doing testing. All right, and it has to be below a certain G. Well, you figure the crash, the adult is going 20, the G-force about 20. All right, well, when they hit, they're, as soon as they hit, there's some payout, and then they start riding down as soon as they hit the seatbelt. Okay, so it's pretty much automatic for them. The payout and the ride down all go across that top bar, and then until they finally come to a rest. Okay, the ride down doesn't start for the child seat until all that payout is done. So the child restraint at that point may hit up to 60 G's because they're still going forward. That adult's being restrained by a seatbelt. The child is strapped to a car seat and it's coming forward or rotating or whatever it's doing. We want to minimize that payout because then the ride down can start. So there are a lot of different things. Obviously, we're not talking about cars today, but when it comes right down to it, the better installation to the vehicle does help the child seat with ride down, whether we like to admit it or not. That's what it's all about. The vehicles are designed with crumple zones and all kinds of energy mitigation things that we need to take advantage of. And we don't, because we have the seat that's too loose, and when the payout comes out, it's too much. All right, so again, I've already said this, I'm going to keep going. Remember, the vehicle also has that ride down effect. It also has payout, which is the metal crushing. So again, we want to make sure we minimize that stuff. So if we can, we have to figure out how to minimize that payout. Well, if I do a child seat with just a seat belt, no base, all right, I can do this without the European belt routing. But if you think about what does a European belt routing does, it helps energy management without the base. It basically does the same thing as a load leg, it limits that downward rotation. It doesn't limit it as much as a steel bar to the floor. It still limits it. So that, again, in itself is a limitation or a energy management force. Okay? Not all seats have this. Not all rear-facing infants have the European belt routing. Some of them do. This is out of an owner's manual that shows where the European belt routing works. Now, some problem is, and we've all run into it, where the seat belt's not long enough. And that is a problem with some of the American-made vehicles or American brands. But that's changing over time, just like the load leg, just like the European belt routing was never here before either, and now it is. All right, let's talk about anti-rebound. And I know, and I've seen, and I'm going to say this tongue in cheek, so don't get mad. Social media is evil. All right. And on social media, you see people every day saying, anti-rebound bars are so much safer. You got to have a car seat with an anti-rebound bar. Even in today or this morning's presentation, Julie Mansfield said that there's not really a lot of data that says there's injury from that type of crash or from the rebound. And rebound panels, when you start designing seats, all right, we go back to Brian and say, well, how do you design a seat? You need to put your money where you get your best bang. In other words, where you get the best protection. And that's the key, where everybody is more comfortable. Now, I will say this, an anti-rebound bar does exactly what it's supposed to do. Sits up against the back of the seat and gives the seat more stability and eliminates any type or most motion that could injure a child rebound. Is it the cat's meow? Probably not. Okay. And a lot of people say, why doesn't Nuna Rava have, or why doesn't the Nuna, have an anti-rebound bar? All right. Because the Canadian one does. Well, the Canadian one does because it's required in Canada, even though the data doesn't necessarily point that it's necessary. So in the United States, when that was designed, it was designed to maximize other things that are really more prevalent as far as injury mitigation and energy management. Okay. We've had many crashes using the Rava where rear-ended, rollover, whatever, and the seat does flip up, all right, during that crash, and the child was protected, never touched their head, never touched anything because of the design of the seat. The only reason why it's that way in Canada is because it's required. It's also redesigned completely, so it's a different seat. So when you look at anti-rebound panel on that relaxed base, when you offer all this energy management stuff like the leg and the rigid anchor, and now you have an anti-rebound thing, you definitely have something that manages an energy in a crash. A major thing that actually manages what happens in that crash. But again, what it really does is it gives the sense of a much better install. It does definitely help with making it fit the vehicle better. It makes it one with the vehicle, which is nice. So it is a good thing. So when you look at rebound, and I said there's very little, rebound is just a reactive motion. Okay, I know I only got a few more minutes and I'm almost done. It's a reactive motion in the opposite direction. And look, this is a data point. The first hill is the original crash. The second little blip is just that. It's a blip in this computer. The third one is the actual rebound impact. Guys, look, it's about 1/3 of the initial impact. So it's kind of like, hello, there we go. What's the difference between a rubber ball and a ball that is, like a soft, squishy type ball, okay? A memory foam. A rubber ball, when you hit it on the ground, it stores up that energy and releases it, it bounces back up. A memory ball actually hits the ground and just goes plop because it just absorbs the energy. A rebound bar is only 1/3 because there is no rebound. There's very little. And that's not Tony Teresa there from Cal. That's not him, okay? So, or it could be. So this rebound, if you jump on a diving board, it can't come back up and rebound as much as it went down to begin with because it would hit you in the butt. So it's 1/3 of the crash load. So the need is maybe there, but not as much. So again, anti-rebound bar works in rear, it works in basically rear facing car seats, which is where it's used. And it's 2/3 less. The load is 2/3 less rear rebound. And it's usually non-injury level type crashes. So when you look at this, all of this, and I know it's sprayed out in the back, that's our standards for the HIC values and the different things, okay? We want to reduce the chance of impact. If HIC values or head injury criteria has to be under 1,000, okay? For our infant, all the way to the right, guys, energy management, look, we're at 390. That's a good number. They're going to sell that seat. But remember, there's a lot of different energy management things. There is honeycomb pieces. I don't know if anybody saw, and I hope they did, Tony's little presentation about his car seats. And they had that little foam piece underneath the lap belt portion of the webbing of their car seat. And he says, it's not packing. It's not packing. It's energy management. Energy management comes in a lot of different forms. The foam is energy management. The honeycomb pieces that are made out of plastic that are on the Britex, those are energy management features. These big features that we can see is what I've talked about. Bottom line, every seat made have all of some type of energy management feature, and they all meet a certain standard, and they're all safe. The problem is we still got to get them into those seats. Almost 40% of the children killed or injured are not in anything. And we tried, perfection is great, but we got to get them in it first. So, and I am done. And if anybody, there's my email. Okay. And I think there are probably some questions. I don't know.
Yes, I have a couple questions, Beth. Thank you very much. One of them is, what performance objective do you consider when designing the load leg? Is it the rotation of the seat, or is it the injury values of the ATD, or both?
It's a little bit of both, but honestly, when it comes right down to it, the injury values drive everything. Okay, the injury values is what we're looking at. The load leg, the ultimate goal of a load leg or any kind of energy management thing is to reduce the injury values. So we got to look at those first and foremost. If it doesn't, if we try it without the leg and it's at a certain number, and we try it with the leg and it's at a much lower number, God, you got to go with the leg. Even if they're both passing. But again, that's up to the manufacturer. So everybody looks at it a little bit differently, but when it comes right down to it, bottom line is, what are the injury numbers? I hope that answered. I don't know.
I hope so.
I hope so. If it didn't, let me know.
Yeah, exactly. Are there any vehicles that prohibit the use of the load leg?
Absolutely. I know that.
And why?
Huh?
And
Absolutely.
why? Why is that?
Well, the reason why is because, you know, when you're talking about a load leg, you're talking about crash forces on the floor of a car. Now the question is the floor of the car solid? Like when there's a stow and go open area underneath the floorboard, okay? What do we do with that? Okay, so it's a door versus a floor. So it's a hollow floor that you put storage in. So Chrysler has said, no, you can't do it there. And they don't want it on their floors because they're worried that it's going to crush through their floors. But most floors are a solid piece, that it's not a problem at all. So you have to read the owner's manual. So a lot of the ones that have stow and goes or openings where there's storage and stuff, you don't want to put a load leg there because it's just that. It's a door, not a floor.
Okay. Another question is, am I understanding correctly that payout occurs during rotation, and once these two things stop, ride down happens?
Part of rotation is part of payout, okay? The rotation isn't moving forward. So that rotation is part of the payout. It's pushing down on the cushion of the seat, it's stretching the seat belt, and it's rotating down. So that is part of the payout, is that rotation, okay? When I stop the rotation, there's no more payout because it's not going forward still. When you think about it, rotation is nothing more than it's still moving forward, but it's attached. So it's rotating on that belt or whatever it's rotating on.
Okay. Do you know if there are any other seats besides the ones you mentioned that you can use the Euro belt routing?
You know, you have to look at all of the manufacturers' manuals to find that out. A lot of them will have a piece on the back that indicates that's where the belt goes. I know Cybex has a cut into their seat, into their one of their infant seats, and that's where the belt goes. It depends on the manufacturer. I can't tell you the exact names of all of them. Some of them don't. I know the new Upper Baby Mesa does not have that, but the old one does.
Okay.
So again, it depends on the manufacturer and how they design the seat.
As a parent, would it be, if I could choose between using the Euro belt routing and a load leg, what is your opinion on which is safer?
Well, a load leg is solid. Okay. So, I mean, and again, I guess it depends on if you have a Chrysler with a stow and go seat. I mean, if you have a Chrysler with a stow and go seat, you're not going to use the load leg. You're going to, if you use it without the base, you would use a European belt routing. So I think that just from a practicality standpoint, if everybody would think it from a curbside standpoint, what's easiest for the parent to use? Okay. It's easy to just to lower a leg and put it on the floor than it is to bring the seatbelt around to the back. And even though that's easy too, you got to look at practicality. Can they do that and hold on to a kid? And they wouldn't do it with a base. So unless the seat allows them to do it with a base. So it's up to the vehicle seat. It's up to the parent, really.
I don't have any more questions. Do you, Megan? Okay.
I do not.
All
I
right.
think
Thank
that
you,
is
Bob.
all. Thank you, Bob, for such an informational session. Well, we've come into the end of our conference. So thank you all to our speakers and participants for all of your patience. This was a learning experience for all of us. It was also one big virtual adventure. Thank you for joining us on the crazy ride. Watch for an email from us within the next few days to access the conference evaluation and your certificate for continuing education credits. Remember, the evaluation provides a lot of useful conference feedback for future planning, and it provides useful feedback to our presenters as well. It won't take you too long to complete it either. You may email ocpd@siumed.edu if you have any questions about the credits. Thank you again for taking the time to join our virtual conference. Bye.